to find our domain, we're going to set our Q of X, our quotient, equal to 0. We're going to have to solve and figure out where that is. And then it's going to be everything but that. And so we're going to practice with these a bunch of times. We're going to find our intercepts. We're going to find some discontinuities. We're going to work with some asymptotes. It's going to be a whole thing. But we're going to start with finding our domain. So finding the domain means we're going to have to set whatever is in the denominator equal to 0 and solve that. So if there's x's in the domain, we have to solve that. If it's x squared in the domain, we're going to have to solve that. We're doing factoring. Our favoriteest. We have seen these before, but we spend like a whole chapter on them in Algebra 2. We're going to spend like 2 days on them in Precal. So it's very heavily based on things we've done before, but it's probably going to be harder problems than we've done before. And we go significantly faster than Algebra 2. So it's kind of like math builds on itself. Precal just builds on everything. Okay? Yep, I can go back. Next semester, you will see an absolute ton of new things.
Yay. I mean, I saw some new stuff.
Because we're going to deal with a whole lot of trig stuff next semester. Sine, cosine, tangent.
Oh, I've seen sine, cosine, and tangent.
Yeah, but we're going to have a new style of graphing where it's shaped like a circle.
A circle.
Uh-huh. Vanessa. Oh, but it's not for another hour. You're fine.
Oh, that's the blood donation thing?
Yep, these are blood donation cards. So honestly, they may bring yours is great because yours is 20 minutes before yours. Okay. So our first rational function that we're going to deal with and find our domain on is this guy. So we have f of x equals numerator of 4x squared plus 3x minus 7. Denominator of x squared plus 8x plus 15. So we need to find everything except where qx equals 0. So that means I need to look at my denominator here, and I need to find out when this guy equals 0. So I need to know when x squared plus 8x plus 15 equals 0. When does x squared plus 8x plus 15 equal 0? Yeah, so we're going to factor it. Use our frame. 15 and 8, 5 and 3. Because we can write this in our factored form of x plus 5, x plus 3, right? So x equals -5 and x equals -3, right? Vaguely familiar? So if our domain is everything except those two values, how can I write that? Yep. From -infinity to -5, close it with a parentheses. Union. Well, we're going to have that part too, but we need the space in between. So we need to go from -5 to -3, again with parentheses. Now we can union that with -3 to infinity. Everything except -5 and -3. The only things excluded are -5 and -3. But we're going to always write our domains and range in interval notation. Yes, dear. Hang on, I got to extend it out. Boop. There we go. So we're going to always write it in our interval notation. So sometimes our domains are going to be long because it's everything except where our denominator equals 0. Okay, so, okay on domain? Because next we're going to go on intercepts. Like, we're just going to add things every slide. We're going to add a new thing. Because we're going to talk about our intercepts. To find our x-intercepts, we find the zeros of the numerator. To find our y-intercepts, we're going to substitute in 0 for x. It's going to wind up being the ratio of the constants, but substituting in 0 is the more reliable way to do it in case we have weird things going on. Big drink of water before you go. All right, so we're going to start with this f of x here. I'll zoom back out so we can still see the theorems. So f of x is x squared minus 2x minus 8 over x squared plus 2x minus 15. Thank you. Yep, Layla, here's yours. I knew it was coming soon.
Yay. Yeah, I have like an hour.
Yep.
So
So you just hang on to it. It's just so they don't have it a rush and scramble. And
Oh, I love this person's handwriting.
it's very lovely, very readable.
Look at my name.
All right, so what we're going to do is we're going to find where our numerator equals 0. So we're going to take this guy and factor it to get our x-intercepts. So let's factor that numerator. Multiplies to be negative 8, adds to be negative 2. Well, multiplies to be negative 8 and adds to be negative 2. Negative 4 and 2. So when we put this in our factored form, we're going to have x minus 4, x plus 2. Ah! Yeah. I fixed that. Ah, wrong pen. So our x-intercepts are where? 4, 0, and negative 2, 0. So this has 2 x-intercepts. Why are you whistling? To find our y-intercept, which we should only ever have 1, we substitute in 0. Zero squared minus 2 times 0 minus 8 over 0 squared plus 2 times 0 minus 15. Negative 8 over negative 15. Is that going to simplify it all? It's just going to be 0 and 8/15. So our y-intercept is kind of gross, but that's what it is. While we're here, let's also do our domain. Just to keep practicing all the things. We're just going to add a piece on. So to find our domain, we have to figure out our denominators, zeros. So we got to factor this guy too. So I'm going to do that one in blue over here. Negative 15 and positive 2. going to multiply to be negative 15 and add to be 2. 5 and negative 3. So we're going to have x plus 5, x minus 3. So what can my x's not equal in my denominator? 3 and negative 5. So our domain, when we write that out, is from negative infinity to negative 5, negative 5 to 3, and 3 to infinity. Yeah, so it's when we're in factored form, it's going to be the opposite sign. If you set this piece equal to 0 to find the value. So it's always going to have the opposite sign of what your factor is. We're going to do the same thing on the right one. We're going to find our intercepts and our domain. This one we don't have to factor. It just looks a little bit different. Because it's not in P of x over Q of x form. This is in like a transformation form, which we'll get to eventually. Going to give us a little wall right there. So right now I don't have a numerator I can find zeros of. But could we maybe figure out a way to combine some like terms? Because we've worked with things like this before. What can I do to be able to get the 2 inside my fraction? Common denominator. So this is going to be 2 times x plus 3 over x plus 3. So to write this as something that we can do this with, we're going to have f of x. Our common denominator is going to be x plus 3. What's my numerator going to be? Negative 2x. I hear debate. I have a positive 4, negative 2 times 3. So positive 4 minus 6, minus 2. Sorry, my handwriting is terrible on that. Let me fix that. Yeah, so I just, let me give me a little space to the right. I distributed out, I'm just looking at the numerator here. We have 4 minus 2x minus 6 in our numerator. Okay? Cool. So let's find our x-intercepts. Our x-intercepts are the zeros of the numerator. What I did is green. X-intercept. What is the 0 of our numerator? Yeah, because we add 2 and then divide by negative 2. So our x-intercept is negative 1. And we only have 1. What's our y-intercept? So let's see, y-intercept. That's when we're going to substitute in 0. So 0 minus 2 is negative 2. 0 plus 3 is 3. So as a point, my x is 0. My y is negative 2/3. You were thinking domain. So y-intercept, we substitute in 0. For our domain, it's where our denominator is 0. So the y-intercept and the domain are tricky to keep straight. That's why we're going to practice these over and over again. So our domain is when our denominator is 0. So what is the one thing that x can't be here? X cannot be -3. So the way we're going to write this is from -infinity to -3 joined with -3 to infinity. It's everything except the value of -3. So these have lots and lots of pieces, and we're not even done adding things yet. So these have lots and lots of pieces. So questions here. We found the -3 by looking at our denominator whenever x plus 3 equals 0. So whenever our denominator equals 0, we'll have an undefined function. That's how we find the piece that x can't be. Okay? Ready for the next thing? Because the next thing we're going to add is a discontinuity. I promise they're not bad. There's just a lot of things. We've worked with them before. So removable discontinuity, also known as a hole. So this is our new function. I'm just trying to make it so you can see it. There we go. So here's our new functional. This is the new one we're going to do. We are going to find our domain, x-intercept, y-intercept, and this time we're going to have a removable discontinuity. So what we have, a removable discontinuity, is when we have a common factor in your numerator and your denominator. So that means we need to come through here and we need to factor these. So let's factor the numerator. Multiplies to be 8, adds to be -6. What's our pair of numbers that multiplies to be 8 and adds to be -6? -2, -4. So x minus 2, x minus 4. Hey, guys. Can you stop with having conversations while I'm talking? It is super disrespectful to the people around you. Whether or not you need to pay attention is a whole other situation, but it's super rude to the people around you. And your conversation is loud enough, I could join in. Which means absolutely everyone in this room can hear it. If it's about what we're talking about, that's fine, but it's not. All right, so let's do our denominator then. So we need a pair of numbers that multiplies to make -12 and adds to make +4. 6 and -2. So we have x plus 6, x minus 2. Okay? So what do we see that happens here when we have it in factored form? The x minus 2's will cancel out, leaving us with the x minus 4 over x plus 6. What that tells us is that we have a hole or a removable discontinuity where x equals this. What is the root for this factor? 2. It'd be really handy if we could find the y value for that point. And we can. if we take the leftover bits and substitute in our x equals 2. So we're going to have a whole when x equals 2 and y equals 2 minus 4 over 2 plus 6. So 2 minus 4 is negative 2. 2 plus 6, 8. So negative 2 over 8, negative 1/4. Yes, sir.
How did you get the 2 and the x equals 2?
The x equals 2?
Yeah.
It came from this piece that we canceled out. Yeah. So I would just write it down. Just basically x minus 2 equals 0. So that's the removable discontinuity we're going to add in. So then we're going to go find all the other things we had. So we're going to find our x-intercept. Our x-intercept is the zeros of the numerator. So what's our x-intercept here? Just look at the one after we simplify. 4. So we have an x-intercept at 4, 0. Our y-intercept, substitute in 0. When x is 0, what do we have? Yeah, because 0 minus 4, we have negative 4. 0 plus 6 is 6. Negative 4 over 6, same thing as negative 2/3. Our domain is going to be the same thing as we still got to use our full factor even before the whole. So our x cannot be 2 or negative 6. Because we're going to have a whole at 2. So it's not going to be a huge deal there, but including for our listing, we got to have it there. So our domain is going to be from negative infinity to negative 6, from negative 6 to 2, and from 2 to infinity. So we're practicing these lots and lots of times. We're just adding a new piece in each time. Okay? Just because there's a lot of things to juggle here, and it just takes practice to keep track of things. Okay. Ready for another one? Okay. I'll give you a second to write it down because I know there's a lot of pieces here. I know there's a lot of pieces here. We're almost to the last piece. We have two more pieces, but one of them has 3 options. So we have asymptotes and end behavior left. End behavior has 3 options. So we're going to start with vertical asymptotes. That's going to be our next one. Ready? Okay. I just wait until we don't have anybody that says no. So our vertical asymptotes are our non-whole factors in the denominator. So if it's a whole, it's not an asymptote. But if it's not a whole, it is an asymptote. That's so weird. On my screen, it does not have a V in the word vertical, but on your screen it does. That's so weird. Oh, I can't do that because that looks weird on your screen. Well, if you watch the video, just know there's a we. It's not an vertical asymptote. It's a vertical asymptote. On my screen, it says vertical. it does not have the V. And if I draw it, it draws another V up there. So it's just weird. Weird. I don't like it. I don't like it. Oh, I have a solution. Ha. If I erase that one. Better. Now both screens have a V. Haha. And only one. All right, so vertical asymptotes, we're going to set each factor in the denominator equal to 0. So we got to factor this guy. And we're going to do all the things. So let's factor everything. So let's factor our numerator, factor our denominator, factor all the things. Whoop, highlighter. So let's factor our numerator. So we need a pair of numbers that multiplies to make negative 28 and adds to be positive 3. Negative 4 and 7. But I cannot just hop straight into my factored form since we have that A value. You either need to factor by grouping or toss it in a box. I'm going to factor by grouping just because it takes up less space on the screen. 4x squared minus 4x plus 7x minus 7. So putting this into factored form, we're going to have our 4x with x minus 1 and 7 x minus 1. So our factors are 4x plus 7 and x minus 1. I'm going to rewrite that just because that was horrible. There we go. Way less awful. So then let's factor our denominator.
I have a question.
Yes, dear.
Why did you put 4x plus 7 instead of x minus 4 and x plus 7?
Oh, because we have this A value of 1, we cannot just take these two values. We have to factor by grouping. Because if I take x minus 4 and x plus 7 and remultiply it, I won't get this. So you have to, when you have an A value, either have to factor by grouping or put it through a box. Because our factors are different. They're the same thing as x plus 4 or x plus 7 and x minus 4. So you got to do something when you have an A value. When you don't have an A value, so like for our denominator, we can take the shortcut. That was the wrong button. So when we have no A value, we can absolutely just take what's in our x frame. So pair of numbers that multiplies to make 15 and adds to be 8. 5 and 3. This one does just give us x plus 5 and x plus 3. So be super careful on our factoring. It is super easy, super duper easy. And I've had a lot of people fall into that trap where we stop doing the middle step on the factoring and just take the shortcut every time. But if you have an A value, you have to finish factoring the right way. Please. Okay, so now we've got it in factored form. Do we have any removable discontinuities? No. So to find our vertical asymptotes, we're going to have 2. It's where our denominator is 0. So where are our vertical asymptotes? Yep. So we're going to have a vertical asymptote where x equals negative 5. And since it's a vertical asymptote, we're going to write it as a line. X equals negative 5. It is a vertical line. That is the equation for the line. And x equals negative 3. So these are our vertical lines. We usually draw them as dashed lines, if you remember that from Algebra 2, which we will get into graphing these eventually tomorrow, in fact. So we're going to need that then. So let's do all of our things. We're going to find our domain. We're going to find our x-intercepts. We're going to find our y-intercept. So our x-intercept are the zeros of the numerators. Zeros of the numerator. There we go. Right tense. So our x-intercepts so the zeros of the numerator, where are zeros of the numerator? 1, 0, and -7/4, 0. Our y-intercept honestly, this is going to be easiest to do in the OG, in the original one, over here. You can absolutely do it here, but it's going to be a lot harder math-wise. So 0 plus 0 minus 7, 0 plus 0 plus 15. So when x is 0, our y is -7/15. So in our pre-factor form is where it's going to be easier to find your y-intercept. We don't have any removable discontinuities. We already find our asymptote, so let's do our domain. And our domain is very heavily based off our asymptotes. Those are our two values that x can't be. So we go from -infinity to -5. From -5 to -3. And from -3 to positive infinity. Questions on any of the pieces up to here? Okay. So what we'll do is, oh, yes, dear.
So for the y and x intercept, did you get them again? Like, what did you tell me to get the numbers?
So our y-intercept, we substitute in 0 in place of x. For all x's. So I recommend using the original function we get that's in the multiplied out form, because we then have 0 squared plus 0 minus 7. That's where the minus 7 came from. 0 squared plus 0 plus 15 over the 15. Our x-intercepts are our zeros here. So when we have it in our factored form, we solve x minus 1 equals 0. That's where we got our 1. 4x plus 7 equals 0. And that's where we got our -7/4. Okay? So x-intercepts are the zeros of the numerators. The y-intercept is what happens when we substitute in 0. Cool, cool. So what we'll do is we'll write down our options for our end behavior, but I'm not going to rush us through finding end behavior today. So this will be our last slide that we write down. So our end behavior is also going to be an asymptote. It's either going to be horizontal or a slant asymptote. And you may not have seen slant asymptotes before. I was like, you may have. I know we don't do it in regular algebra 2, but you might do it in honors. So I don't know. So our options are going to be based on what degree we have, what difference in degrees. So we're going to think about P of x and Q of x. P of x being our numerator, Q of x is our denominator. So, okay, cool. So we're going to think about our degree. Remember, our degree is our biggest exponent. So if the degree of our numerator is bigger than the degree of our denominator. So if the degree of P of X is bigger than the degree of Q of X, this is when we have our slant asymptote. Or you may see it written as oblique.
That was a muscle. Your obliques. Really? Am I wrong? Am I correct?
I had the other word in my brain, and then you said oblique again, and it disappeared.
Sorry.
No, it's okay. But I think there are obliques muscles, but that's because they run at a diagonal.
Oh, interesting. Okay. So,
But so oblique just means slant. It's just the fancy word for slant. I think. I don't know. English is a silly language. If the degree of P of X is equal to the degree of Q of X, we're going to have a horizontal asymptote. And what it's going to wind up being is a line at y equals the leading coefficient. I'm going to put LC because I don't have a ton of space up here. Of P over the leading coefficient of Q. So whatever our number in front is. If our degree of P of X is less than the degree of Q of X, so if we have a bottom heavy, this is going to have a horizontal asymptote, but it's going to be at y equals 0. So if we have more x's on the bottom than we have at the top, we have y equals 0. If they're exactly equal, we're going to have it at a different number. And if it's at the top, we're going to have a line. So we will work with these tomorrow. We'll work with these tomorrow. And we'll work with these on Friday as well. Yes, dear. No. It'll just be like the find all the solutions problem.
What unit, were like what, 4 point what?
1 and 2 is what the quiz is over.
Oh, okay.
Which is the find all possible solutions, find all roots. Beastie beasts. What's up? 3 and 4? Is it 3 and 4? Oh, it is 3 and 4. You're right, looking at the wrong thing. So 3 and 4. We've already done 1 and 2. We already took that quiz. 3 and 4. It was just still to find all solutions. I was just thinking the wrong number. Technically. The find all solution. The find all possible roots. Big Beastie Boys from yesterday, like from. I did. Did you enjoy Halloween? Did you have fun?
I was outside.